So, hi Dr. Ariel, this is my oral report on mathematical epidemiology. I'll discuss three papers which I've been walked through. The first one for week 9 is the population biology of infectious diseases, which I discussed. I'll put on the discussion board. The second one is on the computation of RO and its role in global stability. And the last one is a simple vaccination model with multiple endemic states. So the first paper goes into an introduction into the different types of microorganisms. They are categorized as microparasites and macroparasites. So microparasites are the big ones, which is the small ones, which is viruses and bacteria and protozoans, while the big ones, which you can see with your naked eye, is the macroparasites such as herpes infections. So one of the key things about this paper is that it tries to characterize the transmission dynamics of infectious diseases. How does microparasites interact with a population, a natural population? A simple mouse model is used to illustrate that. For instance, the introduction of mice into the population, which is seen as the birth, the removal or the death of microparasites of mice, and all that would affect the number of people in the population at any given time. So, in applying that to creating a full model of an infectious disease transmission in a community, some key points were made on how microparasites can regulate the number of people in the population. And for this to happen, it would mean that the case mortality rate has to be high relative to the intrinsic growth rate, amongst other conditions. So the paper also talks about the population consequences of immune response. And one of the things, and in this case, immune response would mean herd immunity. Would a microparasite still regulate the population during herd immunity? And in what situations would it not be able to, for the disease not to be maintained? And it says that the disease is not maintained and the population grows at an intrinsic 3% rate if the disease in itself is below a threshold value. So again, there are other conditions such as if the duration of the immunity to infection is short and of medium length, then in that case the disease is maintained and disease is able to regulate the population. Epidemic and endemic patterns of diseases are described. An epidemic pattern is when there is a spike in the number of cases of a disease, and after which the infection would disappear for a long time. And then an endemic infections that persist for a long time within the population. So, in describing some of these, what endemicity and in epidemics would look like, the paper also addresses in what conditions would a disease be endemic or be epidemic. I don't want to go into details because of issues of time. So, but the conclusions from this paper is that the effects of a microparasite on the dynamic of populations or an animal population, it depends on the ecology of the interactions between host and parasites, of which there are some key factors, which are the hosts providing the habitat, the degree to which the host can induce mortality, amongst others. I think this is very important to epidemiology because one of the key things that you wouldn't want to happen as an epidemiologist is for a microorganism to completely wipe out the population or to completely wipe out a community. The role of an epidemiologist is to understand how can you prevent such events, how can you prevent premature deaths. So understanding what the impact or the likely impact of a microparasite on a population is really critical. And understanding at what level, using some of the parameters given in this paper, would an infection get to before it will become an endemic or before it will become an epidemic. Take for instance Ebola. Ebola now is currently endemic to some countries in Africa where it previously wasn't found. So we were seeing flare-ups even after it's the World Health Organization has declared that the fight against Ebola is over. So the second paper, which is on the computation of RO and its role in global stability, is really what it is. It talks firstly about some history behind mathematical epidemiology, how Sir Ronald Ross, the guy that won the Nobel Prize for malaria, was able to found the field of mathematical epidemiology by being able to establish some of the first ideas around the threshold phenomenon, which he said, as I quote, that is not necessary, and the paper says that it's not necessary to drive a vector, in bracket mosquito population, to extinction to eliminate malaria. So this really is the basis of the threshold, that at a certain point, when you are able to decrease the number of vectors to a certain point, you don't have to kill all of them, but you only need to decrease them to a certain point and they will dissipate, or in this case be eradicated. So RO is one of the biggest concepts in mathematical epidemiology, and one of the key things to understand, I understood here, is that RO is the average number of secondary cases that an infected individual would create during his infectious period when the infection or the infected individual introduces the infection into the population. So a key way for computing RO in the past was the use of the eigenvalues of the Jacobian at the disease or infection-free equilibrium. But it seems that as time went on, a new approach or different approach for computing RO was using the next generation operator approach. So RO, which the formula for getting what RO would be, is similar to what we've seen in the videos. It is the spectral radius of the next generation matrix. So most of this paper focused on derivations of RO for different scenarios. And one of the things I noticed in the paper was this assumption of proportionate mixing, which I also saw in the derivation for a HIV-related model. And the way I understand it is that proportionate mixing is an assumption of equal mixing of the population. So for the applications of RO, firstly, as based on the definition, it is for understanding how many secondary cases are generated as a result of introduction of an infection from an infectious individual into a susceptible population. But surprisingly, it was interesting to see that this paper also spoke about the concept of optimality and how RO application can be applied in deriving the optimal number of, for instance, the optimal vaccination age, as well as to help guide policies around vaccination for participants and those that need the vaccination at that point in time. So this is a very high level paper with lots of derivations, lots of equations, but also it is kind of understandable, on what the paper is trying to convey. And in relation to how is this relevant to what I'm studying, really, RO is a very, very important number for any epidemiologist. Understanding what the impact of an infection would be in a population is critical. A last thing that I will add is also the issue of global stability, which I'm not really sure that I understand, but to a reasonable extent, the global stability conditions, according to the paper, is when RO is less than 1, is less than 1. So in this case, you are at the disease, so having a disease-free setting is when RO is less than 1. So that means that the disease will die out. And that is to be able to have that, and for that to be stable, RO has to be less than 1, and there is disease when RO is greater than 1. So there is the disease-free equilibrium in itself is unstable when RO is greater than 1. So this is what I really do understand from the paper. I think I think as time progresses, I think it would become more and more applicable to what I do on a daily basis. At this point, this is very, very theoretical. But some of the other concepts that were also discussed in the paper are issues of backward bifurcation, which we would talk about in the next paper. So the final paper is this one on a simple vaccination model of multiple endemic states, which I thought it would be interesting to mention because of the concept of backward bifurcation, which was briefly mentioned in the previous paper on the compilation of RO. And I wanted to report on how backward bifurcation can affect planning for vaccine programs and what the relationship with that and RO. So backward bifurcation is defined as a situation in which when RO is less than 1, the disease-free and free equilibrium still remains unstable. So you have a disease even when RO is less than 1. So in that kind of situation, for any individual that is interested in eradicating disease in a population, will have to get to a point for you to be able to remove or eliminate a disease. That disease has to, be eradicated to a point that is way past the point of RO less than 1, such that you will be able to find a point. It's called hysteresis. So it has to be decreased to another point. So meaning that there are two endemic states in this phenomenon. So I'm not sure if I'm very clear on how I explained backward bifurcation, but the endemic states for RO less than 1 is impossible for an invasion to succeed or for an established endemic state to proceed with RO less than 1. But during backward bifurcation, there is endemicity when RO is less than 1. So disease-free equilibrium is unstable. So this is a phenomenon that seemed to be, a huge topic as at the time this paper was written. And there were explorations. The paper tried to explore how this could impact vaccine coverage. So this means that when you're trying to vaccinate people in a system or in a community where there are multiple endemic equilibrium, so just trying to decrease your disease below the normal threshold of R less than 1, or will not be sufficient to ensure that disease is wiped out. So, and even in some cases, it might be a point it might actually lead to increased infection.